Hello, Professor Michael Smart here again. In this presentation, we look ahead to the future of scramjet-powered flight. Recent scramjet flight vehicles such as HyperX and the X-51 have proved that scramjets can fly. The key challenge for the future is to extend flight times so that practical missions can be accomplished. In the not too distant future, one such mission could take off from Northern Australia. Here we are at Australia's new spaceport in far north Queensland. On the launch pad is the Spartan vehicle. Spartan stands for Scramjet Powered Accelerator for Reusable Technology Advancement. It's a reusable vehicle for launching small satellites into orbit. It's the second flight for Spartan this week. Today it's launching a remote sensing satellite to sun-synchronous orbit, which is 450 kilometres above the Earth. The rocket booster launches Spartan on its way north over Papua New Guinea. The first stage booster has done its job. Spartan is now at Mach 5 scramjet takeover speed. The scramjet engines now fire up, and it's on its way under its own power, flying at hypersonic speed like a plane. As Spartan accelerates, the shockwave it generates at its nose becomes stronger. Its outer skin begins to heat up to as much as 2,000 degrees Celsius. The third stage rocket and the satellite are nestled on its back, protected from the hypersonic environment. Spartan has now reached its maximum speed of Mach 12. The final stage rocket fires and pulls away. This small rocket takes the satellite up to its final orbit. Spartan has done its job and can turn around to glide back to its launch site. It lands on a normal runway just next to its launch site. After refuel, it'll be ready for its next flight. So what are the technical challenges that must be overcome to make the Spartan vehicle a reality? Well, there are two main challenges. The first involves the aerodynamic and propulsion design of the vehicle. The second involves the high temperature materials needed for its survivability and reusability. In terms of aerodynamics and propulsion, only the highest performing scramjet flow paths will work. I've discussed some of the key attributes of scramjets in previous presentations. High inlet efficiency, robust combustion, and a low external drag are critical to strong engine performance. Current 3D engines have shown significant promise in meeting these criteria. Of course, the overall vehicle drag must be minimized also. This can only be accomplished with a synergistic integration of both the engine and the vehicle, such that engines with large capture area can be installed. Large capture area means high airflow, which, as we have seen, leads to high thrust. Finally, for an accelerating space access system such as the Spartan vehicle, scramjet engines must operate over a large Mach range. Development of engines such as these is what the hypersonics community continues to strive for. Of course, for a scramjet of any type to fly, it must be made of materials that can withstand the hypersonic environment. So the second future challenge is the development of lightweight, high-temperature materials. The one aspect of hypersonic flight that makes it most different from flight at lower speed is heating. In general, heating rates on an aircraft increase with the square of the Mach number. So heating rates at Mach 8 are 16 times those at Mach 2. One region of extreme heating is at the sharp leading edges of the vehicle. Here is a plot of heating rates on leading edges with decreasing radius, plotted versus flight Mach number on the horizontal axis. The combination of sharp leading edges, that is small radii, and the hypersonic speed leads to extremely high heating and temperatures greater than 2000 degrees C. Research on high temperature materials that can maintain strength at these elevated temperatures has long been the focus in the hypersonic community. Just like any flying vehicle, weight is a critical issue. The following well-known circular argument is directly applicable to hypersonic flight. High weight, coming from a heavy airframe structure, requires high lift. This leads to high drag, which must be overcome by high thrust. High thrust needs lots of fuel, which leads to more weight. So light structures will be needed for scramjet-powered vehicles to become a reality. A final aspect of hypersonic materials is the thermal structural design needed to deal with thermal expansion. As we all know, materials grow as they heat up. Designing a structure that does not break up as its skin heats from room temperature to 2000 degrees C is a major engineering task. In the 1960s, the designers of the SR-71 Blackbird dealt with this by allowing the plane to leak on takeoff. As it heated up on the way to Mach 3, the plane's structure grew together. So in closing, it is important to emphasize that any commercially viable hypersonic vehicle must be reusable. The future challenge for scramjet designers is to develop the technology to make this a reality.